is Evgenios Vlachos, and this is the next presentation. This presentation is about flood image analysis using drone images. First of all, I will introduce the concepts and the growing importance of utilizing drone technology and advanced AI techniques for flood management. We then move into the principles of deep semantic segmentation and flood region segmentation. The next part is object detection, also an impactful application of object detection, which is the person and vehicle detection in flooded regions. Also, house roof detection, which plays a critical role in identifying locations where individuals may be stuck. And finally, I'm going to present a simple application that uses these techniques and feeds one simple flood monitoring system. First of all, we understand that the importance of natural disaster management systems is very critical. As we see in this slide, the catastrophic floods in Thessaly in 2023 reminds us of how unprepared communities can suffer immense loss. Flash floods are becoming more common due to the global warming, and this has created a need for robust systems that can predict the impacts of these disasters. And contemporary natural disaster management systems can use technology, including artificial intelligence and satellite images and data analytics, to provide early warnings and rapid response strategies. For example, AI can analyze vast data sets in real time to predict areas at risk, which allows authorities to implement evacuation plans and allocate resources efficiently. In this slide, we highlight the transformative role of drones in natural disaster management, which are now an important tool because they can access areas that are too dangerous or inaccessible for humans, and allow us to gather critical information during disasters like floods. For example, as we see in the image on the right, it shows a UAV monitoring flood damage in Peru, which is something that ground teams simply cannot achieve. And using state-of-the-art computer vision models, drones are capable of performing advanced tasks such as flood segmentation or person detection and analyze this information in real time. Moreover, thanks to the advancements in edge computing, we can now deploy these computer vision models directly on the UAVs themselves. This is very important because instead of relying on remote servers, drones can process that on the fly, which reduces response times and makes decision-making faster and more efficient. This is an example of flood region segmentation using drone images, which is applied here to a real-world case from Ahrtal region in Western Germany. On the left, you can see the original drone image, and on the right, we have the prediction of a segmentation model, which is represented as a segmentation mask. A segmentation mask is a binary image that overlays the original, marking specific regions of interest. In this case, the black and white mask identifies the flooded areas with the white regions highlighting where flood has occurred. This mask is generated by deep learning models that analyze the visual data pixel by pixel to determine which parts of the image correspond to water or other relevant features. Here I'm going to analyze the mathematical principles of image segmentation. When we perform segmentation, we take an image domain, represented here as X capital, and divide it into n distinct regions labeled as R1 to Rn. Each region corresponds to a specific segment of the image, for example, flooded areas or non-flooded areas or other relevant features. The segmentation is governed by a logical predicate denoted as P of R. This predicate defines the rule that determines which pixels belong to which region. For example, in flat segmentation, the predicate might identify flat areas based on pixel intensity or other visual characteristics. So the segmentation process has some properties. The first rule is that the entire image domain X is partitioned into non-overlapping subsets R1 to Rn, which together fully cover the image. This is shown by the formula X equals union Ri. The second rule of segmentation is that no two regions overlap, which means the intersection of any two regions is empty. The third rule is that the predicate Ri is true for all pixels within region Ri, which ensures consistency in its segment. And the last rule is that the predicate Ri union Rj is false for overlapping regions, which maintains separation between segments. So in simple terms, we are ensured that each region is unique and clearly defined, which is essential for accurately identifying and analyzing flat areas. This slide explains how flat region segmentation works using a process called pixel classification. The idea is that each pixel in an image represented as X is classified as either part of the flat region, which is the foreground, or not, the background. To do this, we use a function f, which generates a segmentation mask. The function works by creating a probability map showing how likely each pixel belongs to a flat area. And this probability, denoted as P, gives a value between 0 and 1 for each pixel. Next, we apply a threshold T to the probability map. If the probability of a pixel is greater than or equal to the threshold, we classify it as a part of the flat region. If it's below the threshold, it's classified as non-flat. This is one of the most used evaluation metrics for segmentation. It is called intersection over union, or IOU. For each class I, IOU is defined as the ratio of the intersection over the union between the predicted mask and the ground truth mask. In other words, it tells us how much the prediction overlaps with the true region relative to their combined size. As shown in the formula, we calculate IOU for class I by summing the overlap across all images, which is the number of pixels that belong to class I in both the predicted and ground truth masks, and divided it by the total number of pixels predicted as class I or labeled as class I in the ground truth. The symbols AK and PK in I represent the predicted and ground truth masks for class I in image K, respectively. Also, we can find this metric as Jaccard similarity coefficient or overlap score. And to evaluate the model over all classes, we compute the mean intersection over union, or MIOU, which is simply the average of all the IOUs across all C classes. To summarize, IOU tells us how well we are segmenting each class, and MIOU summarizes overall performance across all classes. This slide explains how deep semantic segmentation is achieved using advanced neural network techniques. First, we can transform image classification networks by replacing their fully connected layers with convolutional layers. This change allows the network to output heat maps, which are visual representations showing the likelihood of specific regions, for example, flooded areas in an image. Next, we enable end-to-end dense prediction learning by adding extra layers and using a specific loss function. This means that the model learns directly from input images to produce pixel-level predictions without the need to separate processing steps. Finally, we often use an encoder-decoder network architecture for this task. The encoder extracts features from the input image, reducing its size, while the decoder reconstructs these features into a detailed segmentation map. This approach ensures that the final output has the same resolution as the original image, with clear classification for each pixel. Here is one dataset that we used for our experiments, and the name of this dataset is FlatNet, which is specifically designed for post-flood semantic segmentation. The dataset consists of UAV images that helps us in identifying and analyzing flooded and non-flooded regions. On the right, you can see examples of real images alongside their corresponding ground truth segmentation masks. The top row shows a non-flooded image with areas like buildings, trees, and open land are clearly identified in the segmentation mask with specific colors. In the middle row, we see an image depicting flooded regions. The segmentation mask highlights the flooded areas, while other classes, such as buildings and vegetation, are also separated accurately. And the bottom row is another example of a flood scene, where floods are segmented alongside other features like roads and structures. However, one challenge is that in datasets like this FlatNet, floods often create a minority class, as they include many regular water body images, which makes flood segmentation, flood identification more challenging. Here are the examples of another dataset that we used, which is named FlatSeg. The left image highlights rural flooding with vegetation and homes. The center image depicts urban flooding with submerged streets and buildings. And the right image captures people in flood waters near houses, showing the human impact. These are the segmentation outputs generated by one DNN model, which is named CNN image to image. I think, as Dimitri said in the previous presentation. The left column is the input image, which are the original flood images. The middle column is the ground truth, which are manually labeled segmentation masks, which serve as the reference or the correct answers for evaluating the model. And the flooded areas are marked in black, while non-flooded areas are in white. And the right column is the predicted mask. These are the outputs that generated by the DNN model, which is the CNN image to image model. And as we see, the model closely aligns with the ground truth and identifies flood very accurately. Also, this is the output of another architecture called PSPNet, which has approximately the same results as the previous model. Also, this is another example of flood segmentation. This is for the Ahrtal case in Western Germany, and the purple areas Here are represented the flooded regions, as they predicted by the previous model that we used, which was the CNN image to image. And the results are pretty good. And one more example here, with the red are the flooded regions. So the next part of this presentation is object detection. First of all, what is object detection? It's a combination of the classification, where we identify what is in an image, with localization, identify where it is within the image. On the left, there's an example of classification, where the model identifies that the image contains a cat. The middle image is the classification and localization, where the model identifies the cat and places a bounding box around it. And the third image is the actual object detection, where the model identifies multiple objects, cat or dog or other objects, and provides bounding boxes for its detected objects. So in object detection, the input is an image, and the output consists of bounding boxes around detected objects. Each image may contain many objects, and the goal is to identify what and where these objects are. Modern object detection combines classification and localization into a single architecture, and this allows for multi-class object detection, which improves both efficiency and accuracy. So, as I said before, object detection is a multitask machine learning problem that combines classification and regression. The model uses a joint cost function that optimizes, first of all, the classification accuracy, J1, ensuring that the right object class is identified. Secondly, the regression accuracy, J2, which ensures that the bounding box precisely encloses the object. And these terms are also balanced with alpha 1 and alpha 2 weights to train the model effectively. Here we present the non-maximum suppression, or NMS, which is a technique to refine object detection results and eliminate redundancy. When an object detector runs, it may find the same object multiple times, which creates overlapping boxes for a single object. And the solution for that is non-maximum suppression, which filters these redundant detections by selecting the highest scoring box for a category and removing all other boxes that overlap significantly with it. Maybe we can use a threshold, typically 0.5, and repeats the same process for the remaining boxes. So with this process, we are ensured that only the most accurate detection for each object is retained, and we avoid unnecessary duplicates. This is an example of a real-world object detection in action. On the left, we see bicycle detection in a sport scenario. Each detected object is highlighted with bounding boxes. And also on the right, we have an example of face detection in a crowded urban scene. Despite the high density of people, the model that used in that case successfully identifies faces and marking them with correct bounding boxes. These are some of the most popular methods for CNN object detection. First, we have region proposal based detectors such as RCNN, fast RCNN, and faster RCNN, which focus on generating region proposals and then to classify those regions. These are very accurate, but they can be computationally expensive. Then there are the single state detectors, which directly predict object classes and bounding box in a single step, which is faster for the previous region proposal-based detectors. For the single state detectors, some examples include the YOLO family and others like RetinaNet and CornerNet. And finally, we have the transformer-based detectors. One example is the detection transformer, which combines transformers and CNN for end-to-end object detection. Here we have the components of CNN-based object detection architectures. And it has three parts. The first part is the backbone, which is a foundational CNN used for extracting image features, for example, edges, textures, or patterns. And common backbones are ResNet and its variations, MobileNet and PGGNet, which are pre-trained on large datasets like ImageNet, and they capture meaningful features. The second component is the neck. The neck layers sit on top of the backbone and refine the extracted feature maps. These layers combine feature information from different stages of the backbone for better object detection. And the last part is the head, which is where the actual object detection is performed. Like the classification, where we determine the probability of each object class, and the regression, where we calculate the bounding box parameters, the center coordinates, the width and height. Over the years, YOLO models have undergone significant advancements, and each version introduces new technologies and optimizations to improve performance. These improvements target three critical areas: the detection accuracy, the processing speed, and the robustness across a wide range of applications. With YOLO version 10, 11, and 12, we see continuous efforts to balance model complexity with different speed. And in that way, we achieve lightweight, accurate, and scalable object detection. Here we explain the architecture of the detection transformer. The first component is the ResNet backbone, which extracts features from the input image. These feature maps are enhanced with positional encodings to help the model understand spatial relationships. The second component is the encoder-decoder. The encoder processes the feature maps, and the decoder uses object queries, which are learnable embeddings, to focus on regions likely containing objects and predict their characteristics. And the third part is the feed-forward heads, which are the layers that generate the final outputs, the class labels and the bounding boxes. Here we see how we calculate two important performance metrics for object detection. They call it the precision. Both metrics are based on the model's ability to detect objects accurately within images. First, the recall is calculated by determining how many of the actual objects is in an image and correctly detected by the model. To do this, we count all the true objects that the model identifies and divided it by the total number of actual model objects presented in the image. A high recall means that the model identifies most of the objects, but it might also contain many false positives. And on the other hand, precision focuses on the accuracy of the model's detection. To calculate precision, we count the number of corrected detections made by the model and divide it by the total number of detections the model makes. High precision means most of the detections are correct, but the model might miss some actual objects. And we also use a confidence threshold to decide whether a detection should be considered valid alongside with the recall and precision. And if the confidence score of the detection is above the threshold, it is counted in the calculations. Mean average precision or MAP is a standard metric used to evaluate object detection models. We use it after computing the precision values across all these thresholds, and we take their average. This average gives us the mean average precision, which summarizes the model's overall detection and classification accuracy across the different levels of certainty. A higher mean average precision value indicates a model that performs well across a range of confidence level, which makes it more reliable in real-world scenarios. Here we have an example of object localization performance using the intersection of a denoted here as J. On the left image, we see the predicted bounding box with green, which aligns well with the ground truth, which is the red. The IOQ score for that is 0.67, which indicates good localization performance. On the other hand, on the right image, the predicted bounding box does not closely align with the ground truth. As we see, the IOQ score is 0.27, which is not a very good localization performance. Here we see a comparison of real-time object detectors using one well-known dataset, the COCO dataset, focusing on two key metrics: the latency and the model size. On the left, we see how average precision relates to latency. Or in simple words, the latency is the time each model takes to process an image. Faster models have lower latency, but they often trade off some accuracy. On the right, the graph shows average precision as a function of the number of model parameters, representing the model's complexity and size. Larger models tend to achieve higher accuracy, but are computationally more expensive. YOLO versions, including YOLO version 7, 8, and 10, are compared here. And we see that the YOLO version 10 offers the best balance between speed and accuracy, which makes it very suitable for real-time applications. So one important application of object detection is person and vehicle detection in flooded regions. Here we see how we detect people and vehicles using a straightforward approach by using a pre-trained model on the COCO dataset. We see here the architecture of YOLO version 6 small model. And in 2022, it was recognized as a state-of-the-art model for real-time object detection. And in the diagram, we see some key components for the architecture. This slide demonstrates the application of DNN models for object detection and tracking during floods. Specifically here, we used the YOLO version 6 small version, pre-trained on the COCO dataset. And we identified persons that may be in danger. The examples here are from Thessaly floods in Greece, which was in September 2023. And as we see, the model accurately detected persons navigating through flooded streets in boats or submerged vehicles. And here's another example. The red bounding boxes indicate detected persons, while the green boxes correspond to detected cars. In the top left image, we can see accurate detections along a flooded pathway, where both vehicles and individuals are identified. Also, on the right image, the model successfully detected all the persons in the image. And finally, on the bottom left image, the model performance is demonstrated in urban flood scenarios. Again, detecting vehicles accurately. Okay, we now move to house roof detection flooded regions using drone images. The goal of house roof detection is to identify and classify bounding boxes around the roofs visible in an image, and especially in scenarios like floods. A detection function generates a set of bounding boxes where each box specifies the location, width, and height of potential roof. Each bounding box is also assigned a confidence score, which represents the probability that it contains a roof. And to determine if a bounding box is valid, we use again a confidence threshold. If the probability score exceeds this threshold, the bounding box is classified as containing a roof. Otherwise, it is ignored. For our study, 3 main datasets were utilized to support flood house detection. The first one is again FloodNet, which is a collection of images for flood-related tasks. The second one is from a city in Greece called Yanitsa. And the third dataset is called Red Roofs, which was built by using images from Google Maps. And on the left, we see images from the FloodNet. The center part shows samples from Yanitsa, and the third part shows images from Red Roofs. Each dataset captures unique features. For example, the FloodNet emphasizes core floods and submerged areas. Yanitsa offers real-world city layouts, and the Red Roofs provides high-resolution images. This slide shows 2 approaches for annotating images with bounding boxes, specifically for complex shapes like a C-shaped building. The first approach, shown on the left, uses a single bounding box to enclose the entire structure. This method is faster and simple, but it may include unrelated areas like empty spaces, which leads to less accurate object detections. And the second approach on the right uses multiple bounding boxes for its object. This approach has many advantages. First of all, it improves the accuracy of object detection and reduces the unrelated pixels. and also minimizes false detections. However, the trade-off is that it requires significantly more annotation effort for us and increases the number of bounding boxes. Here is the inference results between dead and YOLO version 6 medium for cloud half detection. The YOLO version 6 medium performs faster inference than the detection transformer, and it is more suitable for real-time applications. And overall, YOLO version 6 offers a better combination of precision, confidence, and speed for this task. So after we saw all the details for flood region segmentation and object detection, we now use these techniques to feed a simple flood monitoring system, which is an application that combines all these technologies. This slide highlights our flood monitoring system, which uses deep learning to provide insights into floods. It is designed to operate on edge devices, ensuring fast and efficient processing even in remote locations with limited connectivity. And the system is capable of three main tasks. The first one is the flood segmentation, which maps the extent of flood waters with precision, offering clear visuals of flooded regions. The second task is object detection, where it detects humans and vehicles in flood scenarios. And the third part is the integrated alerts, which combines flood mapping and object detection results and generates real-time rescue alerts for civil protection agents and other emergency responders, and prioritizes areas where lives or vehicles are at risk. Here we see the architecture of our unified flood monitoring system, and it combines the flood segmentation network and an object detection network. First, the input frame, which is a video frame or image, is processed by the flood segmentation network. This network generates a segmentation mask that highlights the areas covered by water, and at the same time, the object detection network localizes specific objects of interest in the sea, for example, humans or vehicles, and provides bounding boxes around them. Then both outputs are sent to an information fusion node. This node integrates the flood segmentation mask and the detected objects, and determine if any detected entities, such as humans or vehicles, are in danger due to the flood. And if the system identifies human in need, send this alert to civil protection agents. So here again we have an example from the Thessal floods, where our system was used to identify critical rescue scenarios. With the red mask, we represent the flood water segmented by the system. And also in the images, we can see how the system detected humans and vehicles using the bounding boxes. For instance, a person in danger is highlighted in the red, and submerged vehicles are identified with green boxes. So the rescue alert is triggered when the model identifies a significant overlap of flood pixels within these bounding boxes, indicating objects or individuals at risk. We are now into the last slide of presentation. Here we see how the system identifies objects like people or vehicles and marking them with bounding boxes again, and calculates in the extended bounding box with the black bounding box the water coverage in the surrounding area. In the image on the left, a person is detected standing in rising water levels. And in the top right image, a boat which carries multiple individuals is highlighted. The system, the flood monitoring system, evaluates not just direct overlaps with flood water, but also considers extended areas for a more comprehensive alert mechanism. So I think that was the end of my presentation. Thank you very much.